In a linear regression model, we take the intercept parameter and the slope parameter to characterize the relationship between two different factors. The slope parameter, if we think about what's actually going on with it, it's going to give us the expected change in our outcome given a change in the explanatory factor. And so any question that you have that is rooted in science, that is about how does the changing one factor impact another factor, can ultimately be framed in terms of questions regarding the influence of different regression parameters, and specifically with respect to the slope parameter of a regression. Because this slope parameter of this regression captures such an important part of the relationship or the association between two factors, it's going to be important for us to be able to answer statistical questions relating to the value of that slope parameter. And so fortunately, we're going to be able to apply t-tests or similar statistical procedures in order for us to answer questions relating to the slope parameter from a linear regression model. Specifically, what we're going to be able to say is that because the slope estimator has a normal sampling distribution, we're going to be able to apply standard t-tests in order to conduct statistical inference regarding the regression parameter. So if we think about, well, what is the slope estimator? The slope estimator beta hat 1 is given by the ratio of the sample covariance to the sample variance of x in a simple linear regression. We're using this to estimate beta 1, which is that true slope parameter. Now, if we either have that the random errors are normally distributed, so if epsilon is normally distributed, or if we have a sufficiently large sample, then beta hat 1 is going to have a normal sampling distribution. So it's going to be normal or approximately normal with a mean of beta 1 and a variance of sigma squared times by 1 over the sum of xi minus its mean squared. And so if we think about what's going on here, right? Sigma squared is going to be the variance of our epsilon terms, right? Beta 1 is the true slope parameter. Everything else comes from our data. As a result, if we standardize this procedure, so we take beta hat 1, subtract off the truth, divide by the estimated standard error here, and this estimated standard error is going to be exactly the square root of our variance, except instead of using sigma squared here, which is typically going to be unknown, we replace that with the mean squared error. Right? And if we do this, then we find that this quantity is going to have a Tn-2 distribution. And because it has a Tn-2 distribution, we can use that sampling distribution for statistical inference. So this result can be used to test hypotheses regarding our slope parameter. So what do those hypothesis tests actually look like? Well, if we want to test the null hypothesis that beta 1 is equal to a constant versus the alternative that it's not equal to some constant, right? Then under the null hypothesis, we can take our test statistic to be the estimated value minus the value under the null divided by the estimated standard error. That's going to give us a Tn-2 distribution. And as a result, if we want a two-tailed hypothesis test, then we can calculate out a p-value by taking the value of the negative statistic plus 1 minus the value of the positive statistic, where we're plugging that into the CDF here. So f is going to be the CDF, right? This is owing to symmetry equal to 2 times the CDF at the negative value, right? And so here f is corresponding to the cumulative distribution function for Tn-2 distribution. We can also equivalently run one-tail tests where we just have to change out our way of computing our p-value. So if we have the null hypothesis that beta 1 is less than or equal to some constant versus the alternative that it's greater, we simply want the upper tail p-value. Alternatively, if we want beta 1 is greater than or equal to c versus the alternative that it's less than some constant, that's going to be equal to just our lower tail p-value, right? So we can take all of the standard results from t-tests and apply them to testing for the slope parameter here. So we can take a look at an example here. In this example, we have a biologist who's studying the relationship between the concentration of a certain plant hormone and the rate of root growth in seedlings. In a sample of 63 seedlings, they find the following regression model. And so then we have this output from our regression table here, right? So we're told that we have our intercept. We're told that we have our hormone concentration, right? So each of these rows is representing one of the factors in the regression model. For each, we're told the beta value, right? So we have 1.4 and 1.5 for estimated beta. We're also told the estimated standard error, right? SE stands for this standard error here. So SE is going to be 0.818 for the intercept and 0.068 for the hormone concentration. We're given some extra information. So the number of observations is 63. So we didn't actually need to be told this. We're told that the estimated MSE is going to be 3.14. If we square root it, right? So sigma is going to be the square root of the estimated MSE. And then our squared value here gives us our coefficient of determination. And so we're given a lot of information sort of compactly represented in this table. We want to test whether increasing oxygen by 1 part per million increases the growth rates of plants by more than 1.3 millimeters per day. Right? So this is a substantive question. If we increase the concentration of this hormone by a set amount, by 1 parts per million, does that increase the growth rate by more than 1.3 millimeters per day? Okay. And so if we think about what we're actually asking here, right, if we remember that with our linear regression model, beta 1 is going to represent the change in y for a 1 unit change in x. And it's specifically a 1 unit increase in x. Okay. And so what we're asking here is that if we increase x by 1 unit, right, if we increase oxen by 1 part per million, how is that going to change the growth rate, right? And the growth rate is going to be y. And so in other words, what we want to say is beta 1 greater than 1.3? Okay. And so that's the question that we're actually trying to ask here. And so we can set that up in our hypothesis testing framework, right? We'll take the alternative, or the null is going to be that, in fact, we do not see such a growth rate. So it's going to be less than or equal to 1.3 versus the alternative that it is greater than 1.3. Okay. And so then we can take our estimated values. We can plug them in to get our t statistic here, right? So t is going to be beta hat 1 minus 1.3 divided by its estimated standard error. Okay. We need to know the t distribution that we're actually dealing with here, and the t distribution is always going to be a t n minus 2 distribution, right? And so we have a t63 minus 2, which is a t61 distribution. Right, so we have sort of all of this information hanging around, and plugging this in, we can calculate out our test statistic here. We can then use the t61 to calculate out a p-value, and we're going to be comparing that to alpha equals 0.05. Right, so we can walk through the actual values of this to solve out this example here. Right, so we want to test, is beta 1 less than or equal to 1.3 versus the alternative that it's greater than 1.3. We have the estimated value 1.5, the estimated standard error 0.068, alpha is 0.05, and n is 63. The null distribution has to be that t61 because we're looking at a t n minus 2 distribution here. Okay. So we can calculate out our test statistic value. We take our 1.5 minus 1.3 divided by the standard error. That's going to give us a 2.941. Since this is going to be a one-tail t-test, we only want the upper tail, right? Because we want to know, is it greater than? So that's 1 minus the CDF at the value that we have here, right? If we want that, we can use R to calculate this out using the PT function, right? And so specifically, we want 1 minus F, so we're going to take 1 minus PT. We plug in that 2.941 into it with the degrees of freedom being 61 to match our distribution here, and that's going to give us 0.0023. Okay, so 0.0023 is less than alpha, and as a result, we're going to be able to reject the null hypothesis. So we can say that since the p-value is less than the level of significance, we reject the null hypothesis. There is sufficient evidence in the sample to claim that the slope is greater than 1.3 at the 0.01 level of significance. We conclude that increasing oxygen by 1 part per million increases the growth rate by more than 1.3 millimeters per day. Right, and so again, we have this substantive question: is the impact of the concentration on plant growth rate at least this much, right? And then what we're able to do is we fit our linear regression model and we turn that into a question about the coefficients in that linear regression model, right? So we think about the model as sort of representing the association between our concentration and our growth rate, and we ask our scientific questions as they relate to the coefficients of that model. You can see another example here. So a chemist is measuring the mass of a chemical of a chemical product that is produced based on the mass of one of the given reactants. They run the experiment for 37 different settings and find the following regression model. And so again, we're given out a bunch of information here, but we want to test, or the researcher is theorizing that every gram of the reactant should increase the product by 2.48 grams. Is this supported? And so what we're asking here is that if you increase the reactant by a gram, that should increase the product by 2.48, right? So we're thinking about this as being the exact same style of question as we had before. If we change X, which is our reactant mass, by 1, how much does Y change by? Okay, and so what we're thinking about is we want to test, is this going to be equal to this 2.48 at the 0.01 level of significance, right? And so we can set this up again, just using our hypothesis testing framework here. We can say that our null hypothesis is going to be that beta 1 is in fact equal to 2.48. We'll take the alternative to be that it is not equal to 2.48. Okay. And as a result, we want to run through this hypothesis test here. Okay. And so what are we going to do? Well, we're going to need to calculate out our test statistic, right? And so that's going to be our estimated beta 1 hat minus 2.48 divided by our estimated standard error. We can get both of those estimated values from our table here, right? And then we're thinking about, well, what's the t-distribution? It's going to be a t(n minus 2) distribution here. So that's going to be a t37 minus 2 gives us a t35 distribution, right? And then we plug everything in. This is going to be a two-tail hypothesis test, so we want our two-tail p-value, and we can calculate that from what's given, right? And so we can work through all of this here, right? We're testing beta 1 equals 2.48 versus it not being equal to 2.48. We have the estimated value is 2.5. The estimated standard error is 0.019. Both of those are coming directly from that table. Alpha is 0.01 and is 37. The null distribution as a result is the t35 distribution. Okay, so we can calculate out our test statistic here. Take 2.5 minus 2.48 divided by the estimated standard error. That's going to give us 1.835. And because this is a two-tail test, we want a two-tail p-value, so we take twice the CDF with the negative value plugged in, so 2 times f at negative 1.835. Okay. In R, we can calculate this out by using 2 times pt. Remember, pt is going to be the CDF of the t distribution here. We plug in negative 1.835 to match this value. Degrees of freedom is 35 because that's what we found before, and that gives us this value of 0.0375, right? So 0.0375 is actually going to be greater than our alpha level, and because it's greater than our alpha level, we're going to fail to reject the null hypothesis at the stated level of significance. So since the p-value is larger than the level of significance, we failed to reject the null hypothesis. And what we're saying there is that there's insufficient evidence given the observed data to conclude that the slope is not equal to, and this should be 2.48, not 1.48, right? We were testing against the value of 2. So to conclude that the slope is not equal to 2.48, thus the researcher has no reason to doubt the theory, at least not at the level of significance that was chosen for this test. So using that normally distributed sampling distribution, standard t-tests are going to be able to be applied for statistical inference regarding the slope parameter in simple linear regression models. And when we're thinking about that, what we're really thinking about is this is going to allow us to test the association or the relationship between two different quantities. So anytime we have a scientific question that is of the form, how does changing x influence the expected value of y, right? We're thinking about that in the context of a linear regression model, and then we're thinking about that relating to a test of the actual value of that slope parameter. Fortunately, once we've framed it through the lens of that model, testing the slope parameter becomes running a standard t-test. So we can run our two-tail test, we can run our one-tail tests, upper or lower. We can be testing against 0, we can be testing against any value that's going to be scientifically relevant. All of that is going to be coming directly from our t-test theory. And so the important question is going to be able to frame that scientific question in terms of the linear regression model, and then determine, well, what is the hypothesis test that we're actually interested in doing? Once we've determined that, it's going to be as simple as running a t-test to get our answer.